This video is going to be other multi-object problems, so not inclines or outwards or anything like that, just other problems. All right, so let's say in this first problem, we have a person pulling a sled on a frictionless snowy surface. On that sled, there is a big present which remains at rest, and there's a coefficient of static friction between the big present and the sled. And then there is a tiny present on top of the bigger present, and that tiny present is able to slide across the top of the big present because it's a nice slick surface. So there is a mu k between those two surfaces. All right. So we have, and the sled is pulled at an angle of theta. Okay. So we have three objects in our system. Okay. We have the sled, we have the big present, and we have the little present. Okay. So let's go top to bottom when it comes to figuring out forces. Okay, so acting on the little present, we have a force of gravity. Let's call the little present A, big present B, C, so we can label these. Okay. We have an upward normal force from the big present. So normal force from big present on little present, or B on A. Okay. Now, as this object is going to slide, or if it's going to slide, it's going to appear to slide backwards. It's not really going to slide backwards. It's inertia wanting it to stay in place. So what's going to end up happening is the sled is going to move under, or the sled in the big present will move under the small present, making the small present appear to slide to the left, which means our force of kinetic friction is going to point to the right. Remember, that's a force of kinetic friction between the surfaces of A and B, the little present and the big present. Okay. So now we have the big present. Okay, remember, there's a little present on top of the big present. Okay, so our fairly obvious forces are force of gravity and a normal force from the sled on the big present, so C on B. Okay. Some less than obvious forces. If there was an upward normal force from B on A, then there is also a downward normal force from A on B. And those two forces are considered a force pair and are therefore equal and opposite. So that's it for vertical forces. Now we have horizontal forces. Okay. So similar, what's the word I'm looking for? Similar reasoning as for the direction of the force of friction of A on B. The force of static friction between B and C, which is keeping the present at rest, is going to be pointing to the right. So if the present is going to slide, it'll appear to slide left, which means static friction has to act right. Okay. Now remember, there's also a force of friction between the interaction of surfaces A and B. So we have our second force pair, right? If there's a force of friction caused by the interaction between A and B pointing to the right on box A, then there needs to be one pointing to the left on box B. And these have to be equal. Okay. And that is it for box B. Then we have C. So acting on C, we have that tension force at an angle of theta. We have the weight of the sled. And we have a normal force from the snow. Okay. Another force pair coming in. If we had an upward normal force from C on B, then there's a downward normal force from B on C. That's a third force pair. Okay, those two are the same. And if there was a static force of friction to the right from B on C, then there is also a static force of friction to the left from C on B. And those two are equal. Okay, so anything that's highlighted here is considered a force pair, which is a cause of Newton's third law. Okay. Now, the sled needs to have some components of tension acting on it. So I'm going to redraw that one real quick, where we have a Tx, Ty, Fn from the snow, a force of static friction between C and B, force of gravity on the sled, and a downward normal force between B and C. And let me highlight those force pairs. And this is yellow. Okay, so the sled is C, big present is B, little present is A. And B and C are connected because the static force of friction allows the two to stay stationary relative to each other. So these two are going to have the same acceleration as each other because they're essentially stuck together through the force of friction. The little present, however, will have a different acceleration than the sled and the big present. Okay, so when it comes to net force equations, that part is going to get a little bit trickier. Okay, so let me zoom out a little bit. So our net force equation in the y direction for A is going to equal 0, which means that the normal force from B on A is just equal to the force of gravity on A, which is just the mass of that little present times G. And then for A in the x direction, okay, we might be accelerating, we might not be. So we're going to leave it as MA, and I should really write this as MAA. And the force that is causing this object to accelerate across the surface is friction. So friction doesn't necessarily always cause us to slow down. In this case, friction is what's going to cause us to accelerate. Okay, so remember, this force of friction can also be calculated by doing mu times the normal force. Okay, where that normal force is the normal force acting on that smaller present, which was the normal force from B on A, which was equal to MAG. So mu MAG is equal to MA. We could use that to find the acceleration of A. So I really should have labeled this as an A the whole time. Okay. So now on to box B, the big box. Okay. So in the y direction, this big box is definitely not moving. So FNCB minus FNAB, since that normal force points down, minus FGB. So this gives us information about what that normal force from block C on, or the sled on the big present is. It is FGB plus FNAB, which, remember, FNAB is one of our force pairs. Okay, so it's the same thing as MAG. Okay, so the normal force between C and B is so far the sum of the two presents, which kind of makes sense. Okay, so then we have a net force equation in the x direction for B. Now, even though B is at rest with regards to the sled surface, the sled is moving, so that means that B is moving as well. Now, we don't necessarily know if it's moving at a constant velocity or accelerating, so we're just going to say that it is accelerating. And I'm going to label this as an A, B, C to remind myself that the acceleration for B and C, the big present and the sled, are the same. So again, we see that the reason why the sled is able to accelerate is because of a force of friction. specifically the force of static friction between the sled and the big present. It's kind of a weird thing friction does sometimes. So that's the static friction minus the kinetic friction between B and A. So we have a static friction between B and C, kinetic friction between B and A. B, A, B, C. Force of static or force of kinetic friction between A and B, okay, is mu times the mass of A times G, or I could write it as the mass of A times the acceleration of A. I'm going to leave it as the mu mass of A times G, and I should have labeled that with a mu K. Okay, so this is going to be minus mu K MAG is MBABC. This force of static friction is the coefficient of static friction times the normal force on B. The normal force on B, okay, we just solved for, is the masses of the two present, or the forces of gravity of the two presents. So MBG plus MAG minus mu K MAG equals MB ABC. Depending upon what I know, I could solve for a couple of different things here. But we're not solving for anything in this. We're just kind of going through how to approach the problem. So the last question, or the last free body diagram we have, is for letter C. Oops. C. And I'll zoom out a little bit so I can see C. So in the y direction for C, we're at rest. We have a couple of different forces. We have a tension in the y direction. We have a normal force from the snow. Those two should be added together since they're both upwards. We have the force of gravity of the sled minus the downward normal force from the bigger present on the sled. Okay. So it's likely that we would know the tension and the angle. So let's go ahead and solve this y direction for the normal force from the snow. So Fn snow is going to end up equaling FNBC plus FGC plus TY. Now, if you remember, FNBC is another one of our force pairs. Okay. So normal force on the snow is going to equal FNBC is MBG plus MAG plus the force of gravity acting on the sled, MCG, plus the y component of the tension, which would be T sine theta. That's fun. So there's our y direction. In the x direction, we are accelerating, we're not accelerating, we don't know. So I'm just going to write this as A, B, C, because remember, the acceleration here is the same as the acceleration here, but not the same as the acceleration there, which is why I gave it its own letter. Okay, so in the x direction, we have a tension in the x direction and a force of static friction. So tension in the x direction minus a force of static friction between the sled and the big present, MCABC. And that force of static friction is our fourth and final Newton's third law force. So the equation that we previously wrote for the static force of friction holds true, which I highlighted. Tx is the same thing as T cosine theta. So this would be minus mu s. So it should be mu s times the normal force, but that normal force was the normal force between B and C. The normal force between B and C was MBG plus MAG. MBG plus MAG equals MC ABC. Again, I could solve for ABC, or the acceleration of the big present in the sled. Okay. You'll notice that my Fn snow is not in the x direction equation. That's because the only time I would need this Fn snow is if there was a force of friction with the snow. which in this case there is not. So I do not need Fn snow. All of my frictions are based off of other normal forces I had previously found. Okay, so now let's go on to a different problem. So in this problem, I have a cat pulling 2 boxes. I should have made the cat push 2 boxes. Okay, we're going to make the cat push 2 boxes so that this problem works the way I want it to. So this cat, hover cat, apparently with very long legs, is pushing on 2 boxes, B and A, and there are coefficients of friction between the 2 blocks that are the same. Okay. Again, 2 objects, so 2 free body diagrams, A and B. We're not going to draw a free body diagram for the cat. Okay. So acting on block A, we have an FGA. We have a normal force acting on A. And we have a force from B on A. Okay, so the force from the cat isn't actually acting on block A. What's going to push block A is a horizontal force from block B. So we're going to call that FBA. And then we have a friction force, a coefficient, or a kinetic friction force, as we're sliding. And on B, pretty much looks the same. We have an FGB. We have a normal force. We have the applied force from the cat. And a friction force. Okay. And then we also have, if B pushes to the right on A, then A pushes to the right on B. And that is a force pair that exists within our system. Okay, so those 2 forces are equal in magnitude but opposite in direction. Because these 2 boxes are stuck together essentially by the fact that they're being pushed against each other, they also have the same acceleration, okay, because they are connected. So in A, my net force equation in the y direction is a combination of a normal force and the force of gravity. Okay. Now, I should have actually written this as 0. My net force is 0 in the y direction. So my normal force acting on block A is just equal to the weight of block A. Similar thing in B. Okay, the normal force acting on block B is just going to equal the weight of block B. Okay? That's because there's no other forces acting in the vertical direction. And then we have our x direction equations. And in the x direction on block A, we have that force from B on A minus a force of friction for A. And then for B, and BA, we have the force from the cat minus the force of A on B minus the force of friction on B. It's MBA. Okay. Again, things that are the same. We have our Newton's third law pair, and our accelerations are the same. So we can use that to help us maybe solve for an acceleration or just simplify our equation. So I could figure out what the force between the 2 boxes are, that FBA force, by adding the force of friction on block A to both sides. That force of friction is just going to be the mu times the normal force on A, which is the force of gravity on A, which is the same thing as the mass of A times G. So I can take this whole equation and plug it in over here. So we have F cat. I'm just moving everything up here for more space. F cat minus, remember to use parentheses, the mass of A times A plus mu MAG. The force of friction on B is the mu times the normal force on B. The normal force on B we already talked about was the force of gravity on B. So MBG equals MBA. Gotta distribute that subtraction. MAA minus mu MAG minus mu MBG is MBA. Move all the A's to one side. Okay, so we get F cat minus the two forces of friction. Nope, that should be a K MPG equals, and once we get all of our A's to one side, we can read this equation as the net force, meaning this whole thing here is the net force, is mass times acceleration. So our net force is the force on the cat minus the two forces of friction. So that FAB force cancels out, which makes sense because they're equal and opposite on both objects. We can factor out an acceleration on the right side, okay, and which then means we need to divide by that total mass. Okay, so our acceleration equation would look like F cat minus mu AG minus mu and BG. And again, these should be mu Ks. I'm pretty sure I dropped them some places. But just remember that those are mu Ks because it's a kinetic coefficient because we're sliding across the surface. NB plus MA. Okay, so that's an acceleration. Again, not always going to solve for acceleration. We might be given an acceleration and need to find the force of the cat. That's how we would approach that problem. Okay, last problem I want to talk about. Let's say we have a dragon dragging 3 different boxes at an angle theta. Okay, so we have 3 strings. So we have 1 tension, 2 tensions, 3 tensions. Okay, and we're going to say that this is a frictionless surface. Because that makes our lives a little bit easier. So we have, let's make this object A, B, C. So acting on object A, we have a tension. Okay, that's T1 specifically, acting at an angle of theta. We have a force of gravity acting on A. We have a normal force acting on A. And then we have a T2. And then for B, we have an FGB, FNB, T2, and T3. Then acting on object C, we have an FGC, FNC, and T3. Now, because this is a frictionless surface, we're actually not going to care about the y direction at all. The only time we care about the y direction with a problem like this is if there is friction, because we need the y direction to find the normal force. So for the sake of time, I'm just going to look at net force equations in the x direction for these free body diagrams. Okay, I'm just going to make one edit to A. Okay, since T1 is at an angle, we need to have components of T1. So I really need T1x, T1y. Okay. So again, just looking at the x direction, again, all of these objects are connected. So they do have the same acceleration because they're all connected. So acting on MA, we have a T1x minus a T2 would give me mass of A times the acceleration. T1x is really T1 cosine theta. Okay, for B, again, just going to look at the x direction. I have T2 minus T3. And then for C, I have the mass of C times that acceleration. It's the same acceleration for every object in the system because everything is connected. So T3 equals mCA. Let's say our end goal was to find that acceleration. And the only thing we knew was T1. So we only know T1, and I need to solve for the acceleration. Okay. So clearly I need to use A because that has T1 in it. But in order to know T1, I need to know T2. In order to know T2, I need to know T3. So I can use C and kind of work my way forward. So if T3 is MCA, I can substitute in for T3 over here. So T2 minus MCA is MBA. And I can use this to find T2. MBA plus MCA. And I can then take this T2 and substitute it in here. So T1 cosine. Remember to use parentheses. MBA plus MCA is MAA. I'm going to distribute that subtraction. Minus MCA. Move these two terms over to that side because, again, I'm solving for acceleration. So T1 cosine theta is all of those masses added together. And I'm factoring out an A out of all of them. So my acceleration is T1 cosine theta over the total mass. Okay. Oops, that should say MC. Okay. So the only force that's going to impact the acceleration of this system is however hard this dragon, that's what that's supposed to be, is pulling. Okay, because this T3 and this T3 cancel each other out. And then this T2 and this T2 cancel each other out. So the only force that we're left with in that x direction to cause a net force is T1x. Okay? Remember, for any system, the acceleration is, still writing a highlighter. The acceleration for any system is the net force over the total mass. So that's what we are left with.